the production function for this economy is characterized by k to the power of alpha times n to the power of 1 minus alpha. Since there's a multiplication sign separating capital and labor, n, we know that we have a Cobb-Douglas production function. In the very first part of the exercise, we have to figure out whether this production function is characterized by a constant returns to scale. If this production function is characterized by constant returns to scale, we know that increasing both input factors by 1% will increase output by the same amount, that is 1%. So since we have a Cobb-Douglas production function, we can just sum the exponents in order to assess whether the production function exhibits constant returns to scale. K is raised to the power of alpha, n is raised to the power of 1 minus alpha. So we take the sum of the exponents, alpha plus 1 minus alpha, and we get a 1. If the sum is equal to 1, then we will have a production function that exhibits constant returns to scale. That means that if we increase both input factors by the very same factor, let's say it is a factor t, then increasing both capital and labor by a factor t will also increase output by a factor t. So bottom line, the production function exhibits exercise 1, question 2 and 3 combined. So are there decreasing marginal returns to capital? Are there decreasing marginal returns to labor? So first we noticed is that we have a production function that is characterized by k to the power of alpha times n to the power of 1 minus alpha. K and n, that is capital and labor, are separated by a multiplication sign. That means that we have a Cobb-Douglas production function. Whenever we have a Cobb-Douglas production function, we know that there are decreasing marginal returns to capital whenever alpha is between 0 and 1, and that is the exponent that capital is raised to. If we have decreasing marginal returns to labor, we must have that the exponent that labor is raised to, that is 1 minus alpha, is between 0 and 1. And this is the case in this exercise, since it is given that alpha is between 0 and 1. So if alpha, for instance, is equal to 1/2, yes, alpha is between 0 and 1, and it fulfills the assumption. Then the exponent that labor is raised to, must be equal to 1 minus alpha, and that is 1/2. Okay, so both exponents are between 0 and 1. Therefore, we have decrease. So in this exercise, we have to transform the output production function into the output per worker production function. And how do we find output per worker? Well, we take total output, that is y, and we divide by the number of workers. So we have the production in the numerator, and we have the number of workers in the denominator. So what was in the numerator? That was the production function. That is k to the power of alpha times n to the power of 1 minus alpha over n. This we can rearrange. This is the same as k to the power of alpha times n to the power of 1 minus alpha over n. This we can simplify. This is the same as n to the power of 1 minus alpha minus 1. That is just n to the power of minus alpha. So we have that output per worker is equal to k to the power of alpha times n to the power of minus alpha. This is the same as 1 over n to the power of alpha. So we have k to the power of alpha over n to the power of alpha. That is the same as k over n, everything raised to the power of alpha. And then we have transformed the production function into a relation between output per worker, that is output over the number of workers, and capital per worker. So now we have a relationship between output per worker and capital. So in this exercise, we have to give an expression for capital per worker in steady state. Remember, when computing the steady state values, we always have to start out by finding the output per worker function. Okay, and this we did earlier. Earlier we got that the output per worker was equal to, still is, k over n to the power of alpha. So in order to find the capital per worker in steady state, we start out by finding the output per worker. We did that in the previous exercise. Then in the next step, we have to recall the capital formation equation. That is the equation that describes how capital evolves over time. This equation here states that capital stock in period t plus 1 is equal to the initial period's capital stock plus investments minus depreciation of capital. So step number 2, we write up the capital formation equation. KT plus 1 is equal to KT plus investments minus depreciation of capital. And then once we do that, we continue to step number 3. In step number 3, we have to use the steady state condition. And that is the condition that states that the capital stock is unchanged from one period to another. That is that the capital stock in period t is unchanged to the capital compared to the capital stock in period t plus 1. In other words, the capital stock does not change from period t plus 1 to period t. So the change in the capital stock when we go from period t to period t plus 1 is 0, meaning that the capital stock is unchanged. So we impose this. So since we are in steady state, we then use that KT plus 1 is equal to KT, and we drop the subscripts because we do not care about the timing in steady state, because everything is constant from one period to another in steady state. So we drop the subscripts. What does that mean? That means that we drop all of these timing subscripts. Okay. So KT plus 1 is equal to KT. Then we have that K cancels out. And then we end up having delta K should be equal to investments. Since we are in a closed economy, we know that savings is equal to investments. Instead of writing Y here, instead of writing investments, we can simply write total savings. Total savings must be equal to total output times the savings rate, which is between 0 and 1. Remember, we choose to save a fraction of our total income. And the fraction that we choose to save is then determined by the savings rate, which is between 0 and 1. So if the savings rate is equal to 1/2, we choose to save half of our income and consume the remaining half of the income. So now we have delta K is equal to the savings rate times output. Then we obtain the following equation here. once we get here, we have to transform this equation in per worker terms. So we need this. We need this in per worker terms. How do I transform this equation in per worker terms? I divide by n on both the left and right hand side. Then we have output per worker. We replace the output per worker with the exact output per worker function that we did find in step 1. So we write delta k over n is equal to the savings rate times k over n to the power of alpha. Now I divide by k over n to the power of alpha on both the left hand side and the right hand side. Why? Because we would like to solve for the capital stock in per worker terms in steady state. And then I also divide by delta on both the left and right hand side. So I get the savings rate over delta. And this here I can simplify. This is the same as k over n to the power of 1 minus alpha. So now we have that the capital stock in per worker terms to the power of 1 minus alpha is equal to the savings rate over delta. And how do I solve for the capital stock in per worker terms in steady state? We raise both the left and right hand side to the inverse of 1 minus alpha. And what is the inverse? Well, the inverse of 1 minus alpha, that is 1 over 1 minus alpha. So raise both the left and right hand side to the power of the inverse. Remember, everything that I do on the left hand side, I also have to do it on the right hand side. 1 minus alpha, it cancels out. And finally, we have that the capital stock in per worker terms in steady state, so this is in steady state, is equal to the saving rate over the depreciation rate to the power of 1 over 1 minus. In question 6, we have to give an expression for output per worker in the steady state. From earlier, we know that the output per worker function is equal to the capital stock per worker, that is k over n, to the power of alpha. In the previous exercise, we found that in steady state, the capital stock in per worker terms is equal to the savings rate over the depreciation rate to the power of 1 over 1 minus alpha. So in order to find the output in per worker terms in steady state, we simply plug in the exact capital stock into the output per worker function. So if we do so, we get that in steady state, the output per worker is equal to the savings rate over the depreciation rate to the power of 1 over 1 minus alpha to the power of alpha. So output per worker in steady state must be equal to alpha over 1 minus alpha. So in this exercise, we have to solve for the steady state level of output per worker whenever the saving rate is equal to 0.32 and the depreciation rate delta is equal to 0.08. Earlier, we found that the steady state level of output in per worker terms is equal to the following. So now we simply just plug in the values that we have, that is alpha, delta, and s. If we do so, we get that the output in steady state is equal to 0.32 or 0.08 to the power of 1/3. 1/3 over 1 minus 1/3. Okay, this here is equal to 1/2. So we have 4. This inside must be equal to 4, and then raised to 1/2. So we have that the steady state level of output in per worker terms is equal to 2. So this was the first scenario. In this scenario, the savings rate is equal to 0.32. That means that 32% of the income is saved and therefore invested in capital. Remember, investments and savings are the same, and investments are put into new machines, new capital stock. In the second scenario, the saving rate is equal to 0.16. So what happens with the steady state level of output? Well, it should decrease. Why? Because now the households, they choose to consume a higher fraction of their income, and if you choose to consume a higher fraction of your income, you'll be able to invest less in capital. And of course, a lower investment in capital will imply a lower level of capital stock in per worker terms. And when we have a lower capital stock in per worker terms, we'll also have a lower output level in per worker terms. So of course, when the saving rate decreases, people will consume more and invest less in capital, and a lower stock of capital is associated with a lower level of output. So we will assume that the output decreases. So 0.16 over 0.08 to the power of 1/3 over 1 minus 1/3, that is 1/2. So here we have 2 to the power of 1/2. That is 1.41, which is less